Hello, my name is Mike Caracas, and this is my oral presentation on the nuclear renaissance, the Westinghouse AP1000 reactor. All right, just a brief introduction. I was in the Navy from 2003 to 2011 as a nuclear machinist mate stationed on the U.S. Dwight D. Eisenhower in the Reactor Propulsion Division, Plant 2. I got out in 2011 and went to work in my hometown at a pump storage hydroelectric facility where I am there today, almost 5 years, and I'm a maintenance coordinator for Oglethorpe Power Corporation. We happen to be partially invested in an AP1000 under construction right now at Plain Vogel. All right, so the AP1000, it is a 2-loop pressurized water reactor, has a gross power rating of 3,415 megawatts thermal, 1,110 megawatts electrical. It has an 18-month fuel cycle, 93% availability, 60-year design lifetime. The AP1000 is simplified design and cheaper to construct compared to its cousin, the Westinghouse Gen 2 pressurized water reactor. It has 50% fewer safety-related valves, 35% fewer pumps, 80% less safety-related piping, 85% less control cable, and 45% less seismic building volume, and 80% less concrete and rebar. So here's a overview of the AP1000 building, of the plant. And here is the footprint of the AP1000 compared to a standard pressurized water reactor plant. As you can see, the footprint is much smaller. Because of those passive safety systems and the less piping, less concrete, the footprint smaller, construction costs are cheaper. The highlighted areas here are safety-related equipment versus our safety-related equipment. So you can see in the older design, the square footage needed for the safety-related equipment is much larger and is also housed all over the site, where it interacts with non-safety equipment. And that interaction reduces the safety equipment's and safety systems reliability. Also, where safety-related equipment is housed, those buildings, the housing, have to be rated to seismic category 1, which is very expensive. With the AP1000, all of the safety-related equipment is housed within 2 buildings, the concrete shielded building and the auxiliary building. All right. The AP1000 is safe, simple, and standardized. Its passive safety systems replace active safety systems, mechanical and electrical systems, which results in less materials and equipment. Its modular design drives faster and predictable construction schedules. Design incorporates vendor-designed skids and equipment packages as well as large multi-ton structural modules and special equipment modules. Modularization allows construction tasks that were traditionally performed in sequence to be completed in parallel. The modular construction techniques are much more cost-effective than stick building the reactor from the ground up. You throw a whole bunch of resources into a construction site, and your diminishing return on production tends to go down. You tend to bottleneck yourself. Now, with modular design, you can create large modules of the plant separately from the site, and as well as in a factory environment. This allows you to build in parallel and as well as increase the quality of the work, as well as drive down the cost of the work. A factory environment is much cheaper to produce in than a field environment. Also, the cost of delivering highly skilled workers to the field is much more expensive than keeping it in-house in a shop environment. And as the quality of the craftsmanship increases, because you're in a controlled condition inside of a warehouse or a factory, the reliability, the quality is a lot better, which makes for a safer plant. Less chance for failures. Now, the O&M costs of a nuclear power plant is 75% of the production cost. So, where, for example, a coal plant's fuel costs are 75% of production, and O&M is only 25. In the nuclear plant, it's completely opposite. So the primary focus, if you want to drive down costs, is to attack the fixed costs of operation and maintenance. So by providing less equipment, or by designing a nuclear power plant that has less equipment, improved equipment, and with advanced diagnostics, your labor and materials to take care of that is driven down significantly. So the manpower, the materials, the man hours necessary to have a preventive maintenance program is all reduced. And the AP1000 expected to have a third less O&M staff than today's operating nuclear power plants because of that. All right. So AP1000, passive safety system. So the passive safety system does not use any pumps, or it doesn't need external power sources. It relies on gravity, natural circulation, convection, and condensation to operate. And drawn from lessons learned across the operating fleet, when they were designing the AP1000, they wanted the requirement that the passive safety systems can safely shut down their core within the first 72 hours of an accident, during a station blackout, without the use of AC power or operator action. And then with some operator action, it can continue to maintain reactor core cooling and spent fuel pool cooling indefinitely. Now, these passive systems provide superior coping capabilities and significantly reduce risk for core damage. For example, the risk of operator error is completely eliminated with a passive safety system because it's all operating autonomously. So the risk of core damage is significantly reduced because of this. So currently, today's operating plants have a core damage frequency of 1 every 20,000 years. The NRC mandates a core damage frequency of 1 every 10,000 years. The AP1000 just blew this out of the water. Its core damage frequency is 1 out of every 1.9 million years. That's pretty cool. All right. So here's a cutaway of the AP1000. Over here is the spent fuel pool. Here's the concrete shield building, the primary containment, the steel containment. Here is the passive core containment cooling water storage tank located at the top of the structure. Needed to be located. I know you're wondering why it's at the top, but that's where it needs to go if you want to let gravity take over and do the work in the event of an accident. So here is the 2 steam generators. There are 4 reactor coolant pumps and a pressurizer. And here's the control room located nice and neatly beneath the reactor core. That probably gives the reactor operator and the senior reactor operator a lot of motivation to safely operate this plant. Not only that, but they're also in a very safe spot from external accidents or threats, such as a missile strike or aircraft impact. So they can safely handle the operation of this plant during that kind of emergency, being tucked away in the safest spot. Now the reactor, the concrete shield building, and the auxiliary building located here are the only 2 structures that are Category 1 seismic buildings, and also contain all these safety-related equipment to handle an accident. So here's the turbine hall and the feed water pumps, and there's the power diesel generator house here. Okay. So the seismic design of the AP1000 building is designed to withstand an earthquake that has a magnitude, an earthquake that would occur every 10,000 years. Not only that, but the AP1000s are only being built in sites that are seismically stable. The construction of the plant is also robust enough to handle natural disasters such as flooding, tornadoes, tsunamis, and hurricanes. The AP1000 can be safely shut down and maintained during a station blackout for 7 days. The advanced passive safety features rely on natural forces such as gravity, natural circulation, condensation, and convection, where the ultimate heat sink is the atmosphere. It has a bunch of power sources. Has a redundant safety-related DC battery bank that supports the safe shutdown for 72 hours. It has 2 redundant 80 kilowatt ancillary diesel generators that provide cooling water to the containment shell and spent fuel pool. The ancillary diesels can run for 4 days with no off-site support. It has 2 redundant 4 megawatt standby diesel generators that can power station service, all the system loads needed to run the place for a period of 7 days with no off-site support. And those 4 megawatt standby diesel generators are not required to cope with a station blackout. The water sources, you have the passive containment cooling water storage tank, as well as the passive containment cooling ancillary water storage tank. The passive containment cooling water storage tank can cool the containment shell for 72 hours, and then the ancillary tank can provide makeup water and extend that coverage for another 4 days, so a total of 7 days. That's just water stored on site. The steel containment is 1 inch and 3/4 thick, high integrity steel, and then surrounded by the concrete shield structure, and the 2 of them combined can withstand an aircraft or a missile strike. The spent fuel pool features a 1 meter thick, heavily reinforced concrete, and it's lined with steel. It can also withstand a missile or aircraft strike. The makeup water for the spent fuel pool can remain covered. The spent fuel will remain covered with water sources located in the spent fuel building for at least 3 days. Following that 3 days, water is provided by the ancillary storage tank. It's a robust design, and it can also withstand all of the natural disasters thrown at it. The control room has a 72-hour air pressurization system and is heavily shielded to keep operators' doses to a minimum. So you talking about the 3 days. So this plant can take care of itself for 3 days, and that gives people plenty of time to get in there and handle any force or active safety systems they need to put in place. All right, so here's the core cooling AP1000 versus standard pressurized water reactor. These core makeup tanks are at reactor coolant system pressure, and in the event of an accident can help provide makeup water to the reactor core. These 2 tanks replace these high head safety injection pumps and also associated piping and water tanks. So this is one of the design aspects that reduces the amount of construction material, piping, pumps, and so forth. All right, so here's the 2 SIM generators and their accumulators. Here is the in-vessel refueling water storage tank. It's located higher than the reactor vessel, and will use, once this is depressurized fully to atmosphere, this tank will then use gravity to force inject water over there and keep the core covered. This layout replaces the low head safety injection pumps and associated piping and tanks. Okay. So standard pressurized water reactor versus AP1000. And here is the this is the primary containment cooling system. All right, so all of this is needed to keep any steam that flashes inside the primary containment condensed and cool. All of this is replaced with just this AP1000 design. The passive core cooling water tank is at the top of the structure, and then because it's located here, it uses gravity to spray water over the structure, which will induce evaporation in the event of an accident. As the primary containment vessel heats up and everything inside it, this will help the heat transfer. And then here's the in-vessel refueling water storage tank, and as you can see here, it is higher than the reactor vessel from earlier. In the event that the core overpressurizes and the pressurizing valves need to dump steam into the tank, this will slowly evaporate and heat up. So whether it core overpressurizes or you have a loss of reactor coolant integrity, the steam that flashes, the primary coolant that flashes inside the structure, will rise to the top and then start condensing. That condensation action, latent heat vaporization is removed, and helps cool down the atmosphere inside here, and but eventually it will overheat, and that's where this system comes into play. So the water being sprayed over the primary containment will assist in removing that heat. It will vaporize, and then hot air rises up and out the top of the building. That creates a low pressure condition around the side, which draws in outside cool air, which goes down and around this baffle plate. And that baffle plate helps this cool air drive all the way down, and so it covers as much surface area as possible of the primary containment structure. So that air will rise and pick up heat and pick up the water vapor that's being created by the primary containment, and then up and out of the core, or up and out of the housing, where the ultimate heat sink is atmosphere. All right. Now the spent fuel pool. As we talked earlier, so the primary cooling or containment cooling water storage tank located at the top of the structure has a backup ancillary tank with a pump, and this is an active safety system, but this is only necessary after the 3 days, and this will help provide makeup water to that tank, and that tank can provide cooling water to the spent fuel pool. The spent fuel pool has an initial volume inside it to keep the fuel pool cool for 3 days anyway, but after that point it will need more water from this tank and this tank. All right. And then when all else fails, there's a number of systems that can also provide cooling water. From the cooling tower basin, so you can throw in river water or seawater. You can use the fire protection water storage tank, which is on site in this pump. You can use the demineralized water storage tank in this transfer pump. You have the tank that was at the top of the structure. You can also bring in a portable pump and use the fire hydrant. So there's a number of sources of water to provide cooling to the spent fuel pool. All right, so here is AP1000 is currently being constructed. The first ones will go online and are being built in China. So they're coming along nicely. Here's Vogtle 3 and 4. 3 and 4 being built by Georgia Power, and is in Waynesboro, Georgia. These are two facilities that my power company are invested in. Here's the heavy lift crane that's used in the modular construction of the AP1000, and the cooling towers are going up beside them. All right. OPC has about $4 billion committed in the construction. We own 30% of Plant Vogtle, so that's just our contribution. There's another facility in called VC Summer up north of Columbia, South Carolina, in Jenkinsville. Pretty cool thing to point out about this is that they're not using the natural draft cooling towers commonly seen at nuclear power plants. They're using a mechanical draft multi-cell cooling tower. Has a larger footprint, but not as intrusive to the skyline. And that concludes my presentation. Thank you for your attention, and looking forward to graduating with the rest of you. Thank you.